I'm going to talk about a lesson today about thin lenses. So we're moving on from mirrors to lenses, and there's a lot of qualities of lenses that are similar to mirrors, but they're unique in a lot of other ways. A lens, unlike a mirror, actually allows light to pass through it, so it's translucent. That means the light goes through it as opposed to reflecting off the shiny surface of the mirror. So we're talking about light that refracts instead of reflecting. So it's a very important difference is that the light passes through and bends in a lens. So if an image is going to be created, it's going to be on the back side of a lens as opposed to with a mirror, it occurs on the front side of a mirror. So there's two kinds of lenses that we're going to study. We're going to study convex lenses and concave lenses. A convex lens is sometimes called a converging lens, and a concave lens is sometimes called a diverging lens, which you'll see why in a minute. The rays pass through the lenses in both cases, and in one case they converge to a point, and in the other case they diverge away from each other as they pass through the lens. Here they're showing you the center curvature and the radius of a spherical lens. So this is a convex lens, it's a spherical lens. So the radius is on the back side here, and on this side, here's your center curvature, and that radius is to the back side of this lens. And you can see the concave lens is just the opposite. Okay. So here's why a convex lens is called a converging lens. You can see the light rays actually converge to a point here on the back side. So if the light rays converge to a point on the back side, they're converging to each other, and you can actually get a focused real image on that side of the lens. So in that sense, a convex lens, which is it's very similar to a concave mirror, because if you remember, a concave mirror is the only one that could create a real image. A convex mirror could only create a virtual image, but with a concave mirror we could create either a real or a virtual image, depending on where we place the object. So in this case, a convex lens would be able to create a real image. Let's talk a little bit more about the convex lens and our three rays. It's really similar to what you're familiar with in the mirror world. So our point or our object is going to be this little arrow over here. Rays come out in all directions. We're going to select three of them to help us locate the image created by this lens. And we've got a convex lens, which means the rays are going to converge after they pass through the lens. So I start with the same ray that we worked with in the mirror world. That's the parallel ray. Comes in parallel to the principal axis. The parallel ray is going to refract, not reflect. It's going to refract through the focal point right there. So it's going to refract through the focal point. And that's our first ray that we're going to draw. We can then draw a focal ray. All right, the focal ray comes through the focal point, refracts through the lens. And by the way, as these things refract through the lens here and here, they obey Snell's law. Okay, so they obey Snell's law as they pass through, which means they'll actually bend towards the normal if we're going from a higher index of refraction or a lower index of refraction into a higher index of refraction material, and just the opposite if we're going from high to low, the ray bends away from normal. So we could figure all that out by drawing the normal line and really zooming in there. We're not going to spend the time to do that right now. But then the third ray is going to be the central ray, and you'll notice all three of these rays. This one, the central ray, comes right through the center of the lens itself, and it passes right along the normal line, so it doesn't refract at all, or it comes in and goes out along the same line. And the image is created on the opposite side, in this case where all three rays converge to a point. That's where the sharpest image would occur. It's inverted, it's smaller, and it's real. Okay, now let's look at a ray diagram for a concave lens. The concave lens is also called a diverging lens. And that's because the rays diverge away as they pass through. So they will never come together on the back side of the lens. You'll never get an image on this side of the lens. Okay, so that's why it's called a diverging lens. And we're going to draw a ray diagram with the three same rays that we had in the last one, the last example I gave you. So here's the parallel ray. Now the parallel ray comes in again parallel to the principal axis, but in order to it's going to refract away again as it comes through. To figure out in which direction it's refracting, you draw a dotted line from the focal point to the center point of the lens and then extend that to the backside. That's the way the refracted ray is going to go. So this is the important part of that ray, though, is on this side of the lens, because we're going to use that to figure out which where the image is going to be created. The next ray is the focal ray. The focal ray you're going to draw again from the same point on the object, but when you draw it, you're drawing it as if it's going through the focal point on the back side over here. So I'm going to draw it. It gets to the surface of the lens, and it passes through parallel, because that's what happens with a focal ray. It comes in as if it's incident through the focal point, only the focal point that you're drawing is towards the focal point on the back side, and it refracts parallel. Extend the refracted ray to the front side. That's the only side where the rays are going to be converging. So you have to actually extend that to the point where it intersects with the other extended refracted ray, which was the first one we drew, and that's where they intersect right there. I could also draw the central ray if I wanted to. It comes into the lens and goes out of the lens on the same path. It goes right through the middle of the lens, exactly through the middle, and that also comes through the same point right here. That's where the tip of my image is going to be. So the tip of the object is over there. The tip of the image is right here. That's a virtual image. It's upright and it's smaller. Okay, this kind of lens can only create images on this side. Okay, now we're going to look at some different ray diagrams for different lenses in different scenarios. These first two are with converging lenses or convex lenses. You can see the only difference in these first two scenarios is where I'm placing my object. In the first case, my object is placed more than 2 focal lengths away. The second case, my object is between 1 and 2 focal lengths away. The difference is the size of the image created. In both cases, you've got a real image that's inverted, but once you move from more than 2 focal lengths away to in between 1 and 2 focal lengths away, the image goes from being smaller, reduced, to enlarged or larger than the object itself. Right when it's at the 2 focal length point, you'd have the image and object exactly the same size. So that's an interesting position. If you remember also that the focal length is exactly equal to, oops, drew that wrong, sorry. The focal length is exactly equal to half the radius of curvature. So if I'm 2 focal lengths away, I'm right at the center of the radius of curvature right there. So when you're at the center of curvature, you're going to actually have an image and an object the same size. So here's when you get inside 1 focal length, a convex lens acts like a magnifying glass. So this is an interesting case right here. So this is the kind of lens that people who are farsighted would wear. So this is older people who need reading glasses, and they're farsighted, so they have basically lenses that make things look bigger. So if your eye was over here, you would see an object that was larger. And basically the parallel ray comes in and refracts through the focal point on the back side. Then you've got your central ray right here that would pass through and come back on this side. You extend those two, and that's how you're going to create your image for the virtual upright enlarged image, and that's a magnifying glass or glasses that are for older people. Glasses for seeing distant objects. We already talked about that scenario right there. But here's a good question. If you had an object and a lens and a screen, and you placed an object, let's say it's a converging lens, and you placed, not a very good converging lens there, but if I had an object out here and it was beyond 2 focal lengths, let's say this is 2 focal lengths and this is F. Actually, I should probably use a capital there. This is 2F. And you covered, half is below and half is above. Okay, so our object's going to be that big. Okay. You cover the top half of the lens. So now I'm going to actually put a piece of paper right here and I cover the top half of the lens. The question is, what part of the image will you see on the screen, the top or the bottom? So if I have a screen over here at the appropriate point, somewhere over here is a screen, and I would have to place that screen wherever I need to move it back and forth to get a perfectly focused image. Which part of the image would you see on the screen, the top or the bottom? So I want you to think about that and keep in mind that rays are reflected in all directions from all points of this object. And you have the bottom half of the lens is still there for rays to strike it. So I want you to think about what would be created image-wise over here. And I think that's one of the questions on your worksheet tonight. Let's talk about the thin lens equation. A thin lens is called a thin lens because its radius of curvature is much larger than the size of the lens. So it's a very gently curving lens, and the thickness of the lens, this thickness right here, if you call that T is much, much less than the radius of the lens. So that's why it's called a thin lens. So a thin lens will behave in the ways that we've talked about so far. Light will refract through it as we've discussed. And this is going to look really, really familiar. This is very similar, in fact, identical to the mirror equation. But now we're going to call it the thin lens equation. The variables are all the same. S is the distance of the object to the center of the lens. S prime is the distance of the image to the center of the lens, and F is the focal length. Okay? You've got 2 focal points or focal lengths and 2 focal points on each side of a lens because light can pass through both sides, and it's the same focal length on both sides. So very similar equation to let us quantitatively determine where images and objects will be located if we know the focal length and one of the other variables. We've got some sign conventions that are important. So several sign conventions. The focal length is positive for a convex lens. That's the converging one that's very similar to a concave mirror. So just like with a concave mirror that can create a real image, a convex lens that can also create a real image has a positive focal length. That means it's negative for concave lenses. That's the one that's kind of curved for nearsighted people. And the only one that's really important for lenses is that the image distance S prime is going to be positive for real images. So if I have a virtual image, it's going to be a negative sign for S prime, the image distance. And that'll be important when we actually start calculating these things. This is probably pretty intuitive, but I thought it was important to add this slide here just to tell you that if you don't put the screen right where the points come together, where the rays come together, you're going to get an image that's smeared over a bigger distance right here, over a bigger area on the screen. So you wouldn't have an in-focus image. And we saw that in the back of the classroom the other day with the concave mirror as we were moving the card back and forth. You only got a sharp image when the screen was placed right where all those rays are coming together. With a mirror, it's on the same side as the object for a real image, but for a lens, it's on the opposite side of the lens for a real image. Let's talk about, real quick about the magnification factor. So magnification factor, this is called linear magnification. There's also a quantity called angular magnification. You don't need to know that for the AP2 exam. So we're just going to talk about linear magnification. And just like with a mirror, it's the ratio of the image height to the object height. So H prime in your textbook to H is the ratio of the image height to the object height. That's also equal to the negative of the object length or distance from the lens to the, image distance to the object distance. That's based on similar triangles. So those are the ratios of different sides of the similar triangles, image to object in both cases. One is distance to the lens and one is height. Notice you got a negative sign in this because if my object is on the same side as the, if my object and my image are on opposite sides with a lens, they're both positive numbers over here, so I'm going to have a negative magnification because of that negative sign in the equation. Well, what does it mean to have a negative magnification? A negative magnification factor means that the image is inverted. So for real images, they're always inverted if you have only a single lens. So my image is going to be inverted, and I'm going to have a negative number in this magnification equation right here. All right, so let's do a quick problem right here. Okay, I've written down the focal length is 10 centimeters, positive 10 centimeters for this convex lens. It has a positive focal length. So I didn't have to tell you that it was positive because always convex lenses have positive focal lengths. The lens is 5 centimeters from the paper. That is the object distance. The paper is the object. The lens is 5 centimeters from it, so we're 5 centimeters for S. And they want us to find where is the image of the insect. We're trying to solve for S prime. The equation looks like this. This is the thin lens equation. And I know two of those three variables, so I'm going to solve for S prime. It's going to be equal to 1 over the focal length minus 1 over S. Okay, I filled in some of the numbers here, and we've got, let's see, 1 over the focal length, 1 over the focal length, 1 over the image distance. It's negative because I subtracted it from that side. So I'm subtracting a larger number from a smaller number. I just kept it in fractions. It's almost easier doing it that way. So I have a negative 1/10 is 1 over S prime. Notice how it's a negative number. So when I invert that, I get a negative 10 centimeters. I don't have to worry about converting to meters because I have all my units in centimeters. So I'm just going to get an answer in centimeters. The negative sign, remember, with a convex lens or in any lens actually means that the image is on the same side as the object. So image and object on the same side of the lens. So that is something that is what you would expect when you have a convex lens where you put the object closer than 1 focal length away. It acts like a magnifying glass. So I've got a negative sign in front of my image distance. And the next part of that means, or the next part of this question asks for the size of the image if the insect is 1 centimeter in size. So the magnification factor, remember, is a ratio of H prime to H, or we can use the image distance and image length in the same way, but with that negative sign in there. So negative S prime is a negative of a negative 10 over a positive 5. So the factor is a positive 2. So if the insect is 1 centimeter tall, the height of the object is 1 centimeter tall, the image is going to be 2 centimeters tall. And it's positive, which means it's real. It's upright. It's a virtual image because it's on the same side as the object, and it's upright, and it's magnified 2 times. Hopefully that makes sense to you. And tonight you're going to do a worksheet 4C, or 5C actually. It's a quantitative practice on using the thin lens equation to calculate object and image and focal lengths. Okay, so have a great distance learning day. See you tomorrow.